So thank you, Edith, Eran, and Ruth, and TCE for hosting this event. But first, I want to also thank the Technion. This is a very special place for me and my family. So the Technion hosts robotics events on this stage, regional events, and 4 months ago, the Technion honored Dean Kamen an honorary doctorate. So Dean, among other things, is responsible for founding the first program, a worldwide robotics competition for inspiration and recognition of science and technology. So now that we're inspired and talked a little bit about recognition, I'd like to move on to talk about science and technology and another topic that's very deeply connected to, which is compilers and SIMD. So I want to present 3 main takeaways in this talk. The first is SIMD is mainstream and ubiquitous in hardware. Second is compiler support for SIMD is necessary. And it's fun, and I have written proof of that, I'll show you. But regretfully, it's insufficient. Okay, and so there's a call to action here to help SIMD become mainstream in software. And to do that with help from compilers, programming language, and tools support, which is already available and continuously improving. So the first thing, hardware is mainstream in SIMD. So if you look at the past decade of Intel Xeon processors, you see that the number of cores grew up, the number of threads grew up, but also there's something called the SIMD width has increased. Okay, and this is all coming from, I guess, Moore's Law, and we're now celebrating 50 years for Moore's Law. So I'm going to concentrate not on the core count or on the thread count, but on the SIMD width, although they are both important. And this is for the servers, but not servers alone. So this laptop I'm presenting from is actually a Haswell laptop. It has 2 cores, 4 threads, and AVX2 with 256-bit SIMD. So SIMD is mainstream and ubiquitous in servers, in laptops, and also in other devices. So the width is increasing, but what does SIMD mean? So in a nutshell, you have like these very wide registers. It's not 32 or 64-bit, it's 256 and even larger registers, and you have quite a few of them. Each register doesn't hold a very large number, but rather it holds several elements. So you could hold 8 single precision floating point values or 4 double precision values in AVX and AVX2. And you can, in addition to the registers, you have the instructions. So for instance, you could add 2 of these registers together into a destination register, and that is equivalent to executing 8 parallel additions in lockstep. Okay? So this is for AVX and AVX2, and for AVX 512 coming up, you have double the number of registers, but also double the width of the registers. So that is equivalent to executing 16 additions in lockstep. So this is very fine-grained parallelism, and the process of converting from a scalar representation of a sort of high-level language, not high-level as Scala, but say C, down to these instructions is something called compiler vectorization. Okay, so we're shifting gears from high-level Scala to Java that Martin talked earlier to sort of the back end of how do we generate code that exploits the hardware characteristics of our machines. Okay, so this is compiler vectorizations. We have these wide registers, and they're getting wider, but not only are they getting wider, there are also many more instructions of them. So if you look at the last 15 years or so of SIMD that has been developed by Intel, starting from SSC, streaming SIMD extensions over to AVX, AVX2, and the forthcoming AVX 512, you see that not only is the width increasing, but the number of instructions is also rising quite rapidly. So now we have thousands of instructions. Depends how you count instructions, but the trend is clear, right? Most of the instructions that the processors have today are vector rather than scalar. Okay? Just a sec. So clearly, proof by construction, you have to have a compiler to support that many instructions, right? There's no other way you're really going to make use of them, okay? So compilers are necessary. I also told you they're fun. Here is my written proof by Shachar Timnat, who worked with us on Intel's OpenCL vectorizing compiler, that it's truly a wonderful, sophisticated ... something I found, simply put, fun. Okay? Now this, you may remember Keren Zender-Hillel's talk yesterday about weight-free algorithms. So Shachar was working with us on the vectorizer in parallel to completing his PhD here at the Technion and doing more of the theoretical work with Erez and with Keren. So this is sort of fun, but I also told you that it's insufficient, right? So wait a minute. Is it really insufficient? So this is an excerpt from Communications of ACM, like about 40 years ago, claiming that Cray developed a Fortran compiler, and it does not require any source program modifications or the use of additional non-standard formal statements to achieve vectorization, right? So haven't we solved this problem 40 years ago? Well, it turns out if you look closely that the optimizing compiler vectorizer innermost do loops. Okay, so what we solved, or what they solved 40 years ago, was how to vectorize automatically innermost do loops. So what are innermost do loops? So this is an innermost do loop, for instance. You have 4 instructions, load, load, add, and store inside a loop. And if you take 2 iterations of them and you sort of reschedule them, you unroll them and you reschedule them, you replace a couple of loads by sort of a vector load or a wide load, and 2 add operations by a SIMD add instruction. Okay, so this is what the Cray compiler was claiming 40 years ago, and additional industrial compilers from Intel and IBM and others have done so as well, and also open source compilers. So Dorit Nuzman from IBM introduced this into GCC about a decade ago, and Nadav Rotem from Apple introduced this into LLVM 2.5 years ago, both of which actually come from Haifa. So clearly, the vector code generation here is pretty straightforward, right? Unroll, reschedule, and then packetize or generate the vector instructions. And the emphasis was really on the analysis and disambiguation to make sure we can move these instructions. You can always unroll a loop, and you can always replace adjacent adds with a vector add. The problem is to do this motion, to make sure that you're not breaking any dependence. Okay? But that doesn't hold anymore, right? Today, it is insufficient. The compiler technology is insufficient to exploit all the opportunities there are. Vector code generation has become much more difficult. So why? If you look today at the code we want to vectorize, we still want to vectorize a loop, but the structure of the loop has many other things inside. It's not an innermost loop. There may be while loops embedded inside. There may be conditionals, and there may be function calls. So if you look at one iteration, it may look like this. If you look at the next iteration, it may take a different direction in each branch. The loop may iterate a different number of times, and when you call a function, well, who knows what happens inside that function? Okay, so ideally what we would like to do is we still would like to vectorize this loop, meaning we would like to unroll it, and then somehow jam it together. Unroll and jam is the term. But this jamming process is not as straightforward as it used to be. Okay, so we would essentially want to execute the brown work together, the blue part of iteration 1 with nothing of iteration 2, and the converse with the red part. The loop will iterate as long as both have something to do. So the first 2 iterations will be complete. The next iteration only, the second, the P1 will have something to do. And then we actually want to perform something like a vector function call, feeding in a pair of x's, getting back a pair of y's, and then executing the 2 together. So we have these fundamental problems, right? We have branches, we have loops. They don't necessarily iterate the same number of iterations. And essentially, we have something that we call diversion, okay? Different iterations want to do different things. They diverge, okay? So it's hard to vectorize what diverges, okay? How do we generate good vector code when different iterations don't want to execute the same thing? Okay, and there are actually two main divergent challenges for SIMD. One is control. A branch wants to take different directions. We can somehow cope with that using predication and masking, as I showed you. And there's also data divergence. You have two different loads. They want to read from different locations in memory. You end up having like these wide gather operations that are less efficient than a wide cache line load or store. So there are many challenges in vectorization today, like doing divergence analysis to make sure whether there is actually divergence or whether you can prove or check that divergence really takes place or not. How to optimize predication and masking, how to handle innermost or outer loop vectorization, and other issues. And the last one is actually what is called function vectorization, where we actually want to deal with a loop that has a function call, like we saw earlier. But wait, if that function has side effects, like it's printing something on the screen, that can cause a dependence between the iterations. And if that's the case, we're not allowed to vectorize that loop at all, because that will create wrong code. So if you have one dependence, it breaks everything, right? So we're sort of at a dead end here. And there's increasing need for user guidance for correctness, so that just to allow us to do the transformation, but also for profitability. Even if we do succeed to vectorize a loop today, we might actually not get gains from doing so. Okay? So I don't want to talk about parallel in the interest of time. The holy grail is just to turn on compiler optimizations like for innermost do loops, and that will buy you everything. On the other extreme, you can use intrinsics if you want to vectorize things by hand. And we spend a lot of time both in improving automatic vectorizers and in providing full support for intrinsics so that you as a programmer can really get your hands on all the performance. But there should be a middle ground. And that middle ground is actually here already in the form of explicit vectorization. And I'll show you an example how that works. So if you have sort of a Mandelbrot function that has a while loop here, but it has dependencies, so you really cannot vectorize this loop. But this Mandelbrot function is being called from a doubly nested loop, and these for loops are vectorizable, but these are two different functions, maybe in two different files, and you need to compile them separately. So what you can do today is you can annotate this innermost function loop with a pragma OMP SIMD, asking the compiler, please vectorize this loop for me. And yes, I know there is a function call here, but it is okay. Trust me, you're allowed to invoke this function multiple times in parallel. And okay, now what do I do when I compile this function? Well, I need some annotations again to tell me, dear compiler, please take this function and generate a vectorized version of it, which will eventually be linked with this caller. So I have separate compilation, but I need user guidance to help me. And that user guidance is already here. I can also parallelize into different threads, and parallelization and vectorization can work together. If I do so, I get considerable speedups. So this is on a Xeon Phi that we saw earlier, and this is not working. So what you see here is that essentially the vectorized code, the serial code is sort of normalized to 1. If you vectorize, you get a 16x speed up, and if you parallelize, you get a 130x speed up, and if you get them together, you sort of get the multiply of the two. Okay, so you really want to both parallelize and vectorize. This is on AVIC on the Xeon Phi. The same thing happens with SSC and AVX2. So we really want to use this capability of annotating functions and feeding that into the vectorizer. So this goes back to the whole idea of whole function vectorization, and a great reference of that is the PhD thesis of Ralph Karnberg from Saarland University, which again expands vectorization across function boundaries, so you can vectorize sort of an enclosing loop of a function. It was originally designed for OpenCL and CUDA and data parallel languages, and with the recent version of OpenMP, I just showed you these OMP pragmas that are already out there. This technique actually comes into mainstream C, C++, and Fortran programming. And last month, or a couple of weeks ago, you have examples published for how to use this. There are a lot of very recent research articles on how to use and optimize whole function vectorization. Ralph's thesis, which is going to be published next month, and this book has a couple of chapters dealing with whole function vectorization, and various conference papers from last year, and some of them are still to appear, that deal with this new and evolving technique. So the techniques are out there, and as I told you, and sometimes the compiler can vectorize it for you. Sometimes the compiler needs these annotations. How do we know if the compiler was successful or not? Thanks for asking, but you can actually ask the compiler. And the compiler is not only a single direction usage, but you can actually get feedback from the compiler. And this is something that has been considerably improved on in recent versions of the Intel compiler, so you can really get feedback from the compiler. Was it able to automatically vectorize something for you or not? And if not, why not? And just by invoking the compiler, you get that feedback. So this is static, but you can also use dynamic tools like vtune and others. And the most recent version of the Intel Advisor has a vectorization advisor capability alongside the threading advisor that it already had before, where you essentially not only have the compiler diagnostics from the static compilation, but also performance data telling you, where are the hot spots and what is the SIMD efficiency. And it can guide you to detect penalties and recommend improvements. And if you're about to go ahead and introduce a SIMD annotation, it can also go ahead and try to check dependence for you and warn you that maybe you're going to cause an error and show you what the memory access patterns are. Okay, so these tools are already available for you. So just to conclude, the main takeaways, the first was SIMD is ubiquitous in hardware. Compilers are necessary, fun, but insufficient by their own. And to help SIMD become mainstream in software, you should embrace explicit vectorization for a number of reasons, and the tools are improving. Last but not least, if you want to hear more, come back to an event we're hosting in 6 months from now, coming to a theater near you. And with that, thank you.